simulation of the war influence. Amir, I guess you're ready, right?
Yes. Can you hear
please.
me all right?
Yeah, please go ahead.
1 second.
Before start, how much time again you will need for
I hope
to present the material?
to be under 10 minutes, but definitely under 15 minutes.
Yeah, you can keep like the goal 15 minutes. Yeah, sounds good.
All right.
Yeah, okay, please go ahead.
You seeing the screen?
Yeah, we can see. Please.
All right. Greetings, everybody. My name is Amir Sanginov. I'm a master's student at the Pukhov Institute for Modeling in Energy and Engineering, and a co-author of this paper titled Resilience of Ukrainian Energy System, Behavioral Simulation of the War Influence, which I will be presenting to you today. Sadly, my co-author, Dr. Alexander Chimiris, could not be present today, and that might impact our ability to answer your questions at the end of the presentation, but I will do my best to answer all of your questions. We will first talk about the motivations for the research, then about the goals, follow it up with a brief description of the model, and finally take a look at the results of the case study simulation, which will also show some of the limitations of the model. The primary motivation for this research is the full-scale invasion of Ukraine by the Russian Federation on the 24th of February 2022, particularly its missile and drone attacks against Ukrainian energy infrastructure, the bulk of which happened between October 10th, 2022 and November 10th of the same year. There is a strong possibility these attacks will continue, or that other countries might face similar predicaments in the future, which puts first and foremost the task of behavioral simulation of the war influence. This is because the actual data regarding the damage done to the grid cannot be shared right now or during the conflict due to security concerns. And so the modeling is required. There is also a question of occupied territories, which can, on one hand, decrease the load on the electrical network, but on the other hand, they can also lower the generation power. The aim of this research is to demonstrate the possibilities of modeling different scenarios of the damage done to the grid and their influence on the energy sector of Ukraine. Such simulation will allow future assessment of the resilience of the Ukrainian power grid. The case study will focus on modeling a step-by-step decrease in generation power capacity as one such scenario and assessing some of the results. The model we use for the simulation represents the grid as a directed graph, which consists of node and branch arrays. Here's the list of the node parameters we have. There are 29 in total. I will explain the colors later. And here's the list of the branch parameters we have. There are 27 in total. Subsequently, configuration is applied to the initial state. Configuration is defined with the parameters highlighted in color and denoted with asterisks. So you can see that we have data that determines configuration topology and configuration parameters. Also, if we go to the previous slide, likewise in green or two asterisks, it's a parameter that defines the topology, and all other colored parameters define the configuration parameters. All right, here is an example of the initial state of the grid. And here it is with applied configuration and also zoomed in. Once the configuration model is created, accounting for the modified configuration topology, we select nodes with fixed voltage magnitude or fixed voltage vector as pivot nodes. Then the electrical network graph is traversed with a breadth-first search, although you can use any search, transforming it into a set of trees and chords. Pivot nodes serve as the roots of the trees. Now we apply configuration parameter to the configuration model. After that, we form the system of nonlinear equations that describe work modes of electrical systems using the mesh current method. We then solved the formed system of nonlinear equations using an iterative method, using power residuals in the nodes being lower than given power values as a convergence criteria. Next, we calculate the additional parameters, such as grid losses, active power flows in the specified sections, and power balance. And finally, we calculate the outputs, voltage magnitudes and voltage angles in the nodes, active power flows at the beginning of the nodes, and active and reactive sums of load and generation. In our case study, we decreased the active generation power by 5% per step from 100% to 10%, while keeping the load constant, which you can see on this graph right here. This decreases voltage, which in turn must be compensated by increase in the reactive generation of the remaining generation nodes, which we also see on this plot. In practice, there will be an upper limit for the possible increase in reactive generation power. And here's where we encounter some of the limitations of the current model, since the characteristics of the generator nodes are not known. However, there's nothing stopping us from incorporating it in principle. It's just that we don't have the data. And even if we did have the data, we still wouldn't show it because of the security concerns. So here I will go back and show that we do have right here above the blue parameters, we have maximum reactive generation level. So it is in the model, it's just we don't have the data for the network. Okay. It's also important to note that this allows us to perform analysis by just assuming different thresholds. Okay, let me go back. So we can assume that the threshold is here, here, or anywhere. So we can just assume. In this particular example, we assume that there is enough reactive generation power, which will reflect on the results later. This decrease in total active generation that leads to the increase in reactive generation also leads to the increase of the voltage angles in generation nodes, which we can see on this slide, and which in turn increases the probability of desynchronization. This final plot shows us the increase of the total number of nodes where voltage magnitude has dropped more than 10% compared to the nominal voltage, as a function of percents of generation power lost. Please note that this is generation power lost, not generation power, as it was in the previous two plots. It's also worth noting that it's not just the number of these nodes that increases, but also the magnitude of the deviation, with 76 of the load nodes having absolute voltage values near zero. For your reference, the total number of nodes is 987, including 413 not under Ukrainian control, and also including the generation nodes, leaving us with a total of 417 load nodes for this case study, which means 36% of the load nodes will be left with insufficient voltage levels at 90% power lost. We see these results because of the absence of the limits on the reactive power generation earlier, which raises the voltage levels and compensates some of the results. So for instance, here, if we did have more limitations, we would see more nodes, potentially all of the nodes, with significantly reduced voltage below nominal, not just 36%. And we would also see the formation of islands. In conclusion, during this presentation, we have described the model for the calculation of the different modes of the Ukrainian power grid, which can be used for analysis of the resilience of the Ukrainian power grid in the future. Using this model, we have tested various scenarios of war influences on the Ukrainian power grid by simulating the damage in a virtual model with a step-by-step process. The case study simulation was conducted with a virtual model of the Ukrainian power grid based on the pre-2021 initial data, modified to reflect the current state of the grid. by applying configuration. Obtained data showed that after losing 40% of the generation power, there was a rapid rise in the number of nodes with voltage levels below acceptable, and at 90% of the generation losses, 76 load nodes lost the power supply completely, and 153 load nodes had voltage levels below acceptable. In the future, we plan to use this model to obtain a better understanding of what constitutes resilience of electrical network, and then use this understanding to improve the resilience. I also have to acknowledge that part of this research and the data shown in the charts was sponsored by the US Army and was accomplished under Cooperative Agreement number W911NF22-20153. The views and conclusions contained in this document are those of the authors and should not be interpreted as representing the official policies, either expressed or implied, of the US Army or the US government. All right, I thank the participants and the organizers of this conference. And with that, we can move on to questions.
Okay, thanks, Amir, for your presentation. It's very interesting. Definitely, we will have some question for you. Dmitry, please go ahead.
Yes, I have two questions. My first questions may be quite difficult.
Okay.
Please explain what is resilience in relation to power supply systems?
That's a really good question. And part of the research we are doing under the contract is trying to better understand and better define resilience. And this study is the first step in this process. So we have created the model. We have done some initial testings, but we will then do additional tests, release more papers, and as a conclusion, in the future, we will define the resilience, and then I will be properly able to answer your question. For now, I can tell you that generally its ability to withstand and recover from various disturbances and challenges while continuing to provide reliable supply of electricity to consumers. But that is a very broad definition. It's not technical, it's not backed up by data, and we hope to change that in the future. I hope that was satisfactory. If you have any more questions, please ask.
Thank you. And another one question. On slide 12, please.
1 second. Right.
What is voltage angle on this slide?
Well, we have a complex voltage.
Yes.
No, the voltage is a complex variable, and so it can be represented in two ways. The first is the real part and the imaginary part, or it can be represented as a magnitude and a cosine angle due to, I believe it's Euler's formula. Well, a complex number could be represented as cosine of the angle and the magnitude. And so that's what the voltage angle refers to. It refers to the complex part as in this angular form. I hope I was able to explain it.
Does it initial phase of voltage?
Yes. It's basically a phase. You can consider it a phase.
Colleague, do you have any other question?
I have
okay.
a question.
Yes, Sergey, please go ahead.
Please show the slide named as initial data, initial conditions.
Here?
And next.
Right.
Okay, I would like to understand the mathematical problem you have solved. You have the topology of electricity system, and you have the nodes with generation units and consumption units.
Correct.
And in the generation units, you fixed the voltage and angle of voltage.
No, only, well, you see these yellow nodes, this means they're fixed by magnitude of the voltage. If they were pink, well, there are currently, well, I can show it to you right now. So here's an example. I know, calculate some mode. 1 second.
It's not possible to see anything in this table.
Oh, don't worry, we will see the graph soon. So here I have changed this. Okay.
Thank you.
This should be, oh my God. Okay. There is a bit of a delay. All right, this should be better. So here I have changed the attribute, and you can see in the tooltips on the right that there are 3 types of nodes. The first is node with a load. The second one is with a fixed voltage magnitude. And the third one, the pink one, with a fixed voltage vector. So it's denoted as V. And now
you fixed the voltage only in the generation nodes or consumption nodes also?
Well, by making it fixed with by making this a node, okay, once again, by changing the node's attribute to V, meaning to the node with a fixed voltage vector, I have just made this node fixed a generation node. So I have changed it. So right now it's a load node. Right now it's a generation node. Right now it's a generation node. So it has some initial data. I'm not sure it's correct because it's it's not based on anything real. And in practice, I mean, in practice, it's not a generation node. So there is some data, and we can calculate it. We can calculate it, and we can see the graph, I hope. And here it is. You can see that it's pink. So this is node with a fixed vector voltage, or voltage vector, I'm sorry. And this is a node with a fixed voltage magnitude. So that's an example of how it works. I hope this clarifies some of your concerns, and we can return back to your question.
And how about, what do you say about the initial voltage in the consumption mode? Do you fix it, or it's a variable that must be determined?
It is a variable that must be determined, but we can fix it. I see what you mean. It is not currently implemented, but it's possible. It's possible to fix.
And this problem have no one solution. There is many solutions of such problem because we simulated the static regime and fixed only the generation nodes voltage. You can find many solutions of similar problem.
Correct.
How to select the solution of this problem?
It is mostly determined by the initial approximation. We start with approximation, and then from there we use an iterative algorithm to converge on the solution.
Approximation what? I'm sorry, approximation what?
Of the solution.
What value your approximation? What?
The balance.
Origin?
We are calculating the balance, basically, the mode.
The total balance between generation and consumption.
Yes, we are attempting to reduce it to 0.
And this solution is arbitrary. It's not. Okay.
We also have some output data. 1 second. There was a slide. So here's the outputs that we obtain. We obtain the let me show it. So we have the voltage module, voltage angle or phase, and then we have power flows, and we have active and reactive generation sums. So these are the outputs as well. We could also calculate losses and active power flows in specified sections. So all of this is the result of the mode calculation. These are the outputs, we can, these are optional. The parameters listed in the additional parameters listed in section 5 are optional. We can, for example, not calculate losses, but these are the main outputs.
And what solver we are using for simulated these static regimes?
I have written my own solver from scratch based on the port system. All right, any more questions?
Sorry, can I ask a question?
Of course, yes.
Yeah. About this slide,
Right.
2 questions.
Right.
First, why you use minus sign between under reactive power Q? Why minus? Why not plus?
As far as I understand, the reactive well, okay, could you please repeat the question?
Does it capacity reactive or inductive reactive power? Why minus sign?
Minus represents that the power is flowing out of the node, and plus represents that the power flows into the node. And this, initially, I have said that the model is a directed graph, and so this sign basically indicates a direction. So generation nodes would have negative active power, and consumption nodes would have positive active power. And the reactive power has the opposite sign of the active power, because it's in the magnetic field. I hope I have answered your question.
Thank you, I understand. And second question, why you use I letter to
and not J?
Not J?
Because I come from a computer science background, and this was more familiar to me. I understand that in the literature they use.
But electrician all over the world using J symbol in this.
Correct. Yeah, it's. Yeah, I didn't think it was important. I can fix it. It's not.
Thank you.
Do we have any other question or comments to presentation? Okay, hearing none. Thanks, Samir, for your presentation.
Thank you.
Let me invite next